Hi everyone, let's solve this problem. Largest rectangle in histogram. Given an array of integer heights representing the histogram bar's height where the width of each bar is 1. Return the area of the largest rectangle in the histogram. Let's understand this problem first. So basically you are given a histogram of different heights and every width of every bar is just 1. So here we have to identify the maximum area of a rectangle. Rectangle can be formed. So this is a rectangle and 2 cannot be expanded further, neither on the left or right. So the area here is 2. For 1, I can expand towards the right and also towards the left, and there are 6 bars. So it is 6 into 1 and the area of this particular rectangle is 6. For 5, I can expand 5 to the next bar which is greater than its height 6. 5 into 2 is 10. For rectangle 6, I cannot expand on left and right because it's the maximum height rectangle. So it is 6 into 1 is 6. And for 2, I can expand it till 5 on the left and till 3 on the right, and the area of this particular rectangle is 4 into 2 8. Similarly, for 3, I cannot expand on any of the sides, so the height of the rectangle is 3 and total area is 3 into 1 3, and maximum among them is 10. That is how we got the answer 10 here. So in order to solve this, we need to find out for any particular, let's say for example I am taking this particular bar, I need to find out a bar which has a lesser height, first lesser height bar than this, so that we cannot continue it. So I can continue as long as I can have a bar which is greater than or equal to this particular bar. So if I can find the smaller bar on the left and also on the right, I will just take whatever is this particular bar. Let's say for example this is the let's say this is left and left smallest and right smallest. I can just increment left smallest to point it to the bar which can be included into my solution, and then right smallest as well, I can just bring it one step before so that I can include, and LS and RS will both be included to give me the area of the rectangle. So we have to find the left smallest and the right smallest element for every bar. That is the task here. So left smallest will be an array with 6 elements, and right smallest as well, it will be an array of 6 elements. Now we are going to use a stack to understand or get the smallest element, left smallest and right smallest. Let's consider this will contain the index. Initially there is no value in the stack, so the left smallest for the first one will be 0. Then I will be inserting 2. Okay, we will be inserting index here, so it will be 0. Its value is 2. This is just for the reference. Then I go to the next element 1, which is a smaller element. That means I cannot expand this particular bar any further, so I can remove my bar from the stack, and when I remove the stack is empty, so the smallest element on left is 0, and then I'll add 1 and 1. Then I'll move to the next bar here, and at this particular bar it's a increasing bar, so 1 can be expanded to 5, so I will just add it. Before adding it, I will also store the whatever is the stack top plus 1 which is nothing but 2 to my left smallest, because on 5 the left smallest is 1, but we are going to store this particular bar because for 5 I can just expand from here as we discussed. So here I will be adding index 2 and value 5. And if you see 6, before adding 6 I will just add stack top plus 1 3, and then I am going to add third index because it's just increasing. Now I get to this particular index 4, which is smaller than 6 and 5. So I'm going to pop both the elements, and then I have 1, and 1 plus 1 will be 2. I will be adding my left smallest element index, and then I'm going to add my 4, and also the value is 2. Then I get a increasing value. 3 is greater than 2, so I just have to add a index. 4 plus 1 will be 5, and I'll just have to insert the index with the value. So this is how we calculated the left smallest. So just to explain what does this mean, let's say for example for 2 I can just, the index is starting at 0 and left smallest it is also ending at 0. For 1 it is starting at 0 and it is ending, it can end anywhere, right? Left smallest it is starting at 0, we can expand any further. For again for the 5 it is starting at second index. Left smallest is nothing but the starting index which we have on the left side. You can call it as left start as well, so that is the reason. And for the 6 it is 3. From here it can expand anywhere. For when we get the right, we will know the right boundary of it. From this we'll get the left boundary. That is what we are doing. Now we will again take the stack. Now we are going to start from the end. We have a stack, this will have index. Now we are starting at this particular index, so the boundary of this will be 5 initially, and then I'm going to add my index 5, value is 3, and then I get a smaller value. That means I cannot expand it any further, right? So what will I do? I will pop this. Stack is empty, so I'll add 5. Then I'll insert 4 index, value is 2. Then I get a greater value, so whatever is there on the stack top minus 1 will be the value in the right smallest, and then I'll be adding my next value. And at 5 it is smaller than 6, so I'm going to pop this particular value, and then stack top is 4 and the value here is top minus 1 3, and then I'll go and we'll get 1 is smaller than 2, so we are going to pop this element as well. Stack is empty currently, so the value here will be 5. And then when I am at 1, I'm going to insert 1 comma 1, and I got a greater value here. So before I kind of insert it, I'll get 1 minus 1, which will be 0. So I'll be adding index 0 with value 2. Now here if you see, so the formula is right smallest minus left smallest plus 1 into height, 0 minus 0 plus 1 into 2, 5 minus 0 is 5 plus 1 is 6, 6 into 1 is 6, 3 minus 2 is 1, 1 plus 1 is 2, 2 into 5 is 10, 3 minus 3 is 0 plus 1 into 6, 5 minus 2 is 3, 3 plus 1 is 4, 4 into 2 is 8, 5 minus 5 is 0 plus 1 into 3. If you see, the values are matching. So now let's try to write the code for the same. So let's have an heights dot length stack will be an empty array, and instead of calling left small, let me call as left boundary array of length n, right boundary of length n. Now let's update left boundaries. I is equals to 0, I less than, and I plus plus. We are checking if stack dot length is greater. We are just checking if stack is not empty, and then heights of I, if it is less than or equal to heights of stack dot length minus 1. So it is nothing but we are getting the index of the stack, that is, and then we are getting the stack top which has our index, and that index we are getting the value of that particular index from heights. Then we are going to pop the value, and if stack is empty, in that case left boundary of I will be equal to 0, else it would be left boundary of I equal to stack dot length minus 1, stack top plus 1, and then we have to push our element I. This will be similar for the right boundary. Before that we have to empty our stack because we are using the same stack for both of them. So it, and also we are starting from n minus 1, it will be greater than or equal to 0, and I minus minus. The same case here, it would be right boundary, and right boundary here will be n minus 1, here it will be minus 1, and where we'll push the value after that, and now we will have a answer which is 0 currently, and then we'll iterate over all the heights, and we'll keep updating our answer with whatever is the max between answer and also the stack dot here we are going to have a heights of I into right boundary of I minus left boundary of I plus 1. This is the value, and we will at the end return the answer. Okay, it should be max, my bad. Let's submit it. Couple of edge cases here. Ensure that you always check less than or equal to, because if it is equal also we have to remove it because we are finding the left smallest bound. And the other thing is like ensuring that you empty the stack before you calculate the right boundaries. These are the couple of things. And the time complexity of this solution is nothing but big O of n here and big O of n here, and also big O of n for this particular use case, but overall it will be big O of n. And the space complexity of this solution will be big O of n for the left boundary, n for right boundary, n for stack, that is all. So n plus n plus n, and it will be big O of overall n. I hope the solution is clear. Thank you.